So now continuing from the ER model that we did in the previous video, let us now look at how do you generate regular lattice models, or what we would call the Watts Strogatz models of small world networks. So how is the regular lattice defined? You have again an n and a k, right. So if you have a regular lattice of size n and k, with it is defined by n and k, what is the number of, what is the average degree of this network? It is going to be twice k. Right. That is what we said. So, so there are basically it is a regular lattice where you are connected to k neighbours on the left and k neighbours on the right. It is always going to be even totally. So, the average degree is going to be even, but k can be any number. So, let us look at a few examples, but before that, what is the logic for creating this network? So, there is this very nice NumPy function called roll, which just permutes an array by just sort of takes the first few elements and puts them at the last, right. And you can do it either, so to speak, clockwise or anti-clockwise by using either minus or plus and things like that. So, this left neighbours identifies the k neighbours of a node to its left, and the right neighbours identifies k neighbours to the right of a node, and there are other ways to do this as well. And now you just look at the neighbours for a single node, you build this list and then just iterate through this list of node neighbours and just connect all of them, right. So, that is all we do. So, it is pretty straightforward. So, what you do is you start with a regular lattice, you just have the nodes and no edges, then you pick a particular node like say 8 and then look at all the k neighbours that are nearest to it, right. And for us here nearest means based on ID. So, 8 is going to be adjacent to 9 and 0 and on the one on the right side and 7 and 6 on the left side. So, you stick them into these lists of left neighbours and right neighbours and then iterate through all the node pairs in this node neighbour array and just connect all of them and you have a graph. So, let us just plot this again and see. Let me just execute this and now plot this. So, regular graph with n equals 10 and k equals 2. So, if I put k is 5, I am going to get like the fully connected graph, right. So, every pair of nodes is now connected to every other pair of nodes, but if I put just 1, I am going to get a simple ring, right, and I can do it for whatever, let us say we do to 20,4. So, you can see that every node will have 6 edges, twice k. This is the regular lattice. Now, how do you actually generate a Watts Strogatz network? How does it differ from a regular lattice? Recall our lecture. We said that you start with a regular lattice and start rewiring it with particular probabilities. So, if your probability is 0, you are going to leave the regular lattice untouched. If your probability is 1, you are just going to mess up all the edges in the regular lattice and you are going to get a completely different network. So, in between this, there are some values of this rewiring probability, which if you remember, I think Watts Strogatz called it beta. So, for some of these values, you will see that the network has very interesting values of both characteristic path length and clustering coefficient, essentially small world properties, which is basically high clustering and low characteristic path length. The low characteristic path length is still sort of similar to random networks, but the high clustering is unique typically to this Watts Strogatz network. It is also present in power law networks and so on, but it is not present in random networks, the high clustering. So, this becomes a defining new feature of small world Watts Strogatz networks. So, now let us see how to generate this. So, we start, so this function Watts Strogatz takes in as input a regular graph, right, a regular lattice, and a probability P of rewiring, and it then basically just picks a bunch of wires or a bunch of edges that it wants to rewire, and it removes the existing edge and then finds a new way to rewire a particular edge, and that's it. Repeat and add all of these edges. And here we are plotting the same Watts Strogatz networks for various probabilities. You look at the p equals 1.0, it's all crazy, very, very different. And you see how there is incrementally higher rewiring as you go from p equals 0 to 0.2 to 0.4, 0.6, 0.8 and 1.0. And note that this is all probabilistic, in that when p equals 1.0, it does not mean that all the old edges have to be gone, right. Some of the edges will still remain, and because you would have done that even after rewiring, you may have connected them during this process of random rewiring too. So, these are all possibilities that you will see. Let us now look at plotting the characteristic path length and clustering coefficient with the corresponding probability values for Watts and Strogatz graphs. Okay. So, what are we doing here? We are defining a function for characteristic path length and a function for average clustering coefficient. Some probability values where we are going to calculate both the characteristic path length L and clustering coefficient C, and this is the regular lattice that we are going to worry about. So, build it, you then you compute the characteristic path length for all the given probabilities, right. So, you produce this network and you find its characteristic path length for all these probability values. You do the same thing for clustering coefficient as well and then plot it. Let us see how this looks like. It takes a little bit time to run because there are at least 10 different probability values. So, you see the characteristic path length spikes for a really low probability value, but then slowly starts decaying, and clustering coefficient starts decaying again and goes to very low values. As you keep decreasing the probability of making an edge between two, as you keep decreasing the probability of rewiring the graph. When you do no rewiring, you are basically that's like 0, that's not on the graph. When you do no rewiring, you are stuck with a regular lattice itself, and you can then have complete rewiring, which is this case, where you have something that's almost random. And so, you do have a zone of probabilities where you have low characteristic path length and high clustering, and this is what is captured in a small world network of Watts Strogatz.